One of the great mysteries of the universe, just because it's just so cool, is what is the nature of black holes? Black holes. Kids love black holes the way they love T-Rex. And I think it's because each of these entities can eat you. And anything that eats you, you give your highest respect. Black holes. You know, they're the consequence of the general theory of relativity of Albert Einstein. And that's his theory of gravity. It's the modern theory of gravity. And it describes gravity not as a force, the way we normally come to think of a force, action at a distance. Gravity is the curvature of the fabric of space-time. Space-time, that's our coordinates in space combined with our coordinates in time. That sounds exotic, but it isn't really. For example, you've never made an appointment with someone at a place unless there was also an agreed upon time. And you've never met someone at a time unless there was an agreed upon place. So the intersection of space and time has been with us our entire lives. It's even in our language. It's just not in our thoughts. These are fundamentally interwoven concepts, space and time. And this whole general theory of relativity concept leads us to the fascinating statement uttered by the relativity community, and it summarizes what goes on. It's that matter tells space how to curve, and space tells matter how to move. Now, what that tells you is that regions of space can have such high gravity that the curvature of space is so deep within it that if anything wanted to climb out of that curvature, it can't. Can't. What's the limit on that? It turns out there's a kind of zone where even if you're traveling at the speed of light, that is insufficient energy to leave the area, to leave the zone. If you are in such a zone and light doesn't get out, and light is the fastest thing we know about, nothing gets out. It is dark and it is a hole. That is what we call a black hole. Now here's what's interesting about that. Here I am on Earth. I can take a pebble, toss it up, it comes right back. If I throw it faster, it'll go higher before it comes back. There is a speed with which I can toss this such that it will never come back to Earth. You can calculate what that is. You can experiment. We've demonstrated it with the missions to the moon. It is 7 miles per second. Now, I'm not strong enough to do that. But I promise you, if I threw this 7 miles per second, it will escape Earth and never come back. That's the escape velocity of Earth. If you have an object that is approaching the dimensions of a black hole, that escape velocity gets higher and higher and higher and higher. And just the way I can play catch with this pebble or with a ball on a very high gravity surface, you can play catch with a beam of light. Because such is the path that the light takes through the heavily curved space-time in the vicinity of a black hole. Now, that makes for some interesting phenomena. What would happen if you fall into a black hole, you might ask? If you didn't ask it, I'm asking it for you. What would happen if you fell in? Well, let's take a feet first dive. All right, so you fall in, there you go. Here's what happens. The center of the black hole, the gravity is so intense that as you get nearer and nearer to the center, because you're falling right now, you get nearer and nearer to the center, the difference in gravity between your feet and your head begins to grow. The difference in gravity. Because the rate of change of gravity is so severe as you approach the center of the black hole. So that difference in gravity we call the tidal force. And tidal forces have the power to stretch things. The moon's tidal force on Earth stretches the oceans, creating tidal bulges. So when you have high tide, low tide, Earth is turning into and out of these bulges. that are always there in space. People say, just a quick aside, the moon affects tides on Earth. Does it affect our heads? Because the tides are water. We're mostly water, the biologists tell us. Yeah, there's a tidal force across your head. It turns out it's 1/trillionth the force on your head that the pillow that you slept with would put on your head if your head happened to be under it. So we have tidal forces. They're especially great across large objects and especially small across the diameter of your head. All right, so here we are falling into the black hole. My feet want to approach the center faster than the top of my head, and I begin to stretch, and I get longer and longer and longer. Stretching feels good initially, but at some point it hurts. And you reach a point where, in fact, the tidal force is greater than the molecular bonds that keep your flesh together, and you snap into two pieces, likely at the base of your spine. After that, those two pieces feel the tidal force, and they snap. So you go from 2 to 4 to 8 to 16. And this continues all the way down to the center of the black hole, where you become a stream of atoms. And that's not even the worst of it. Because space-time is funneling down to a point, you are not only being stretched, you are being squeezed. Shoulder to shoulder, front to back. You're being extruded through the fabric of space-time like toothpaste through a tube. We have a word for this, a word for dying while falling into a black hole. It's called spaghettification. Because that's what you look like, a string of spaghetti falling in. So, it turns out, very large black holes, the tidal force is not as great as small black holes. Because big black holes, your feet, while they're closer to the center, the difference between your feet and the head is not that great. So it turns out you can survive a fall into a black hole. Now here's the kind you want. You want to spin up the black hole and fall into one where when you get inside, the singularity is actually a donut shape. That's what happens when you have a spinning black hole. It takes on extra interesting properties. As you fall into a black hole, time slows down, and to a point where it practically stops. And when it stops, the entire universe that you just left unfolds in an instant, and you see the future of the universe you left in the instant it takes you to fall down into the black hole. This is clearly a one-way trip, okay? Can't tell anybody else about this. But we also learned that you do the calculations for what you expect to find in the center of a black hole that's rotating. There is an entire other space-time that is opened up before you. An entire other universe that's not the one you just came from. So, take a large spinning black hole, fall in for this one-time experiment, and you may end up in another universe entirely. Have we ever done that experiment? No. It works on paper. So we'll accept volunteers. Anybody out there want to verify that prediction?